My name is Abdullah Ismaili and our advisor is Dr. Falak. A little background about the company. Dow Hydraulic is a family-owned company founded in 1967. They manufacture spool and sleeve components for hydraulics, and they also lab and fit hydraulic assemblies. The problem that they're facing is that the current production capacity will not be able to meet the future demand. And the blocker valve is used for the Boeing 737 used to control the wing flaps. The objective of our project is to increase the production capacity from 120 units per week to 168 units per week, and also to detect and remove sources of waste and inefficiency within the assembly. We will be focusing on the assembly line at the Laverne facility.
Now we will transition into the first half of our analysis, which is the current state. We will look at industrial engineering tools to help us solve our problem. First, looking at the blocker process flow, the blocker consists of 35 operations. But here we summarize and group similar operations into 9 major categories. Now we will look at our time studies. Our process and setup times are shown here, given an average of 10 samples. We saw that our total setup time was significantly high, for it was 33% during a shift, and that lapping and scheduled test operations showed signs of bottlenecks. So we looked closer into our testing operation. We created a P-chart to show our sample fraction nonconforming over the span of 4 weeks. Each point on the graph shows the average fraction of failures per set. So we saw here that the nonconforming ratio was 0.35, which is pretty high. And due to the many points out of the control limits, there was no process control. And every time there was a failure, it required rework. And rework took an average of 15 minutes per part.
Looking back at the overall assembly, we created a value stream map to see the non-value added times. Looking at the first 4 processes, we found that the honing is a bottleneck and it's causing inventory in between the processes. And looking at the last 5 operations, as mentioned before, the high defect rate in the testing, and also as to confirm from the time studies, testing, assembly, and lapping are a bottleneck, and they are causing inventory in between the processes. And taking a closer look into the bottleneck operations, which are honing, lapping, testing, and assembly, they have 1 honing worker, 3 lapping workers, and 2 testing and assembly workers. From the graph, the cycle time exceeds the takt time in all these operations, which means that they will not be able to meet the future demand with the current system. So we created a simulation of the current state, and the simulation results are shown in these tables. On the top right table, the average time at location are shown, and the utilization of workers for lapping and honing are 100%, for testing and assembly are 98%. And the time utilization for this system is 67%. This system, they will only be able to produce 120 units per week. Looking at the facility layout, the sequence of operations show the operation that the valve goes through. It starts at storage, goes to electro edge, honing and grinding, then lapping, testing and assembly, then to shipping. We created a spaghetti diagram to see the travel distance traveled by workers. And we found that the total distance traveled by workers per set is 230 feet. Although this number is not significantly high, we also found that the shrink fit and alcohol wash are far from the assembly area.
So summarizing everything that we have learned from our current state, we created this fishbone diagram. Here we listed all of our potential causes and we organized them based on people, environment, and so forth. So to address all the issues related to long cycle time, high scrap rate, no process control, and uncontrolled temperature, we will use quality control. To address issues related to long travel time and worker performance, we will look at a facility redesign. And to address issues related to long cycle time, scheduling, and worker performance, we will look at a new simulation. So now we will first look at quality control. Here is our bottleneck processes, and we created this process chart for you to show that the blocker goes from lapping to assembly and then to test. And recalling from our P-chart, remember that there was 35% of failures in the testing operation, and that required rework. And rework took an average of 15 minutes per part. So we wanted to focus our quality control on lapping. Here we have a blown up view of the valve. There's an A side and a B side. Both sides have a spool and a sleeve. So we created quality control charts on both the sleeve and the spool, and their clearance or their fit between the two. In total, we created 12 quality control charts where we created X and R charts. Now, taking a closer look into our charts, we have our clearances between the spool and the sleeve. On the left side, we have our A side for the R chart, and on the right, we have the B side for the R chart. Here we took a total of 120 samples with a subgroup of 5. And the problems that we found were that the sample points were outside of the control limits, and there was very high variation. So there was no process control for any of the 12 control charts that we created. So due to time and restrictions, we were unable to fix the actual problem, but we created these control charts for Dow so that they can fix the problem now before their demand increases. We came up with a quality control proposal. It's a 5-step plan for process control implementation. The first would be to adopt and implement our quality control charts for a basis so that they can see if the process is out of control. The second would then to be detect the assignable cause for the high defect rate. We came up with 2 assumptions on why we thought the defect rate was so high. 1, it could be the design of the spool which caused leakage in tests, or 2, it was humidity. And with doing a lot of research in lapping, we found that humidity played a major role in the lapping operation. We think that design of experiments would help them to determine their assignable cause. So we came up with 4 factors on what they think they should look at. The type of compound, the type of lap, the humidity, or the RPM of the lathe machine. The third step would then to be remove that assignable cause and make appropriate process changes. Next would be to implement new quality control charts, and then to monitor the process control and the variability. Next, we will look at a facility redesign. So based on the assumption that lapping plays a major role in humidity plays a major role in the lapping operation, we created a new facility layout. The old on the left compared to the new on the right shows that lapping is moved into a controlled room temperature. We then moved shrink fit closer to the assembly area based on their close relationship, and we moved alcohol wash closer to the assembly area also based on their close relationship. So with all of these changes, we were able to move lapping in a temperature controlled room, to move the closely related relationships, and to reduce walking distance by 47%. Although this isn't significantly high, our main focus here for a new design of the layout was to put lapping in a controlled temperature area. So now looking at our cash flow diagram, we have our quality control system and our facility redesign, based on the assumption that we would able to decrease the failure rate from 35% to 10%. So with the quality control system costing about $1,700 and a facility redesign construction costing about $5,000, we have an initial investment of $6,700. And over a time year horizon of 5 years, we have a total net present value of $3.9 million.
And then we modified the current state simulation, and we came up with 2 alternatives that would satisfy the future demand. The first alternative would be to add 1 honing worker, 1 lapping worker, and 1 testing and assembly worker. From the graph, some of the operations some of the cycle times for the operation exceeds the takt time, which means that they will not be able to meet the future demand. However, by adding an 8.5 overtime for 3 lapping workers,